So just learned about average velocity. If you have the average velocity, you look at the change in position over the change in time. That is the difference between where you were at the end and where you were at the start, over the time difference between those 2 points. And we also saw that it was associated with your position versus time graph. It was the slope. And from this, we can also see what the units have to be. Position has units of meters, and time has units of seconds. So the units of velocity are meters over seconds, or more generally, just distance over time. But we can look also, all right, so we have the average velocity. Let's draw in a position graph, something like that. So if we want to get the average velocity, we pick a start point, we pick an end point. So let me label them. Start, end, oops, spell it correctly, end. And then we look at our change in position and our change in time. And the slope of this line gets us our average velocity. But what if we want to look at not our average velocity, but rather our velocity at one particular time, rather than how it changes between 2 times? Well, in that case, we need to go to calculus. We need to do the instantaneous velocity, which is where we have shrunk this time interval smaller and smaller and smaller. So we're walking closer and closer and closer and closer together till this time interval becomes essentially 0. Now, of course, you can't divide by 0, so you have to do some fancy calculus and go to the limit. But what ends up happening is you get the derivative of position with respect to time. And if it's been a while since you've dealt with derivatives, or just in general you've never seen them before, go take a look at the derivative video. But saying you can do the derivative, you will get the instantaneous velocity. It has, of course, the same units as the average velocity, but now instead of being this line between 2 points, it is the tangent line, the line that just barely brushes our position path. And that is the instantaneous velocity at this time point. If we were at a different time point, say this one right here, our starting time point, we'd have to draw a different tangent line, and we'd have a different instantaneous velocity, because right here we're going a different speed and possibly even in a different direction than we are up here. And similar here. We do this, that would be our tangent line. This would be the slope that would give us our instantaneous velocity. All right, so that is velocity. Let's go now look at a change in velocity. So velocity is a change in position, but we can do changes in velocity as well. That is something we are quite interested in physics, and that is the acceleration. So in acceleration, well, we can look at the average acceleration. That is the change in velocity over a change in time. And again, this one depends on 2 time points. Your start and your end. So you need to figure out, okay, what's my velocity at my end time point and subtract it from my velocity at my start point. Similar, and then we have to look at what's the time at the end and the time at the start, and that gets us our average velocity. But if we want to know what's going on in one instant, then we have to look at a derivative. We look at the derivative of velocity with respect to time. And both of these, we can also use those to figure out the units. We have velocity, that's got units of meters over seconds. Time, that has units of seconds. And if we want to get rid of fractions and fractions, well, we're dividing by s, so that is equivalent to multiplying by the reciprocal, which is 1 over s. So the units we use most often are meters per second squared. But remember, this is fundamentally what's going on. It's the change in velocity over time. So it's change in speed every second, but also taking direction into account because acceleration is a vector. All right, so let's look at an example. Say my velocity were this. -2 meters per second to the third times time squared plus 1 over meters second. And I'm going to stop right here and say I really dislike how your book does units in its equation. It makes it a little easier to look at by just putting in the units are going to be whatever the units of the quantity you're looking at. So when they do position, they'll do like x equals some number 4 times t, and then they'll put meters at the end. I don't like that because then you can't do unit analysis. I've done it like this. So here we can check. Let's check out the units and make sure we get velocity. All right, so velocity, well, this one's good. It's meters per second. All right, here we've got meters over seconds cubed. That doesn't sound like velocity, but we also have time squared. So this is meters per second cubed, and the units of time squared is going to be seconds squared. And so we have seconds to the second power, and we're dividing it by seconds to the third power. So that is going to be equivalent to meters seconds squared minus 3, because again, same thing that we're taking an exponential of, so we just subtract the exponents. That means we get meters seconds to the -1. That's equivalent to meters over seconds. So I like my way of doing it, where I put the units in, except for in the variable. I let those units stay in the variable, and I just write the other ones that we need to make this happen. And I'll show you why I like that in just a moment. Just keep in mind I'm doing that differently from the book because it makes it easier for me to double check my work. Okay, so if this is my velocity, what's my acceleration? Well, acceleration is the derivative of velocity. So that means I need to take the derivative of this. All right. So -2, and then meters and seconds are kind of behaving like numbers here as far as the derivative goes. So those guys just came along for the ride just like the 2 did. And then we have t to the second power. So we multiply by 2. And then we have t, and we take 1 power away here. And then this guy's a constant. 1 is a constant. The units are acting like a constant in this situation. So that becomes 0. So the acceleration is -4, 2 times 2, meters over seconds to the third, and then t is to the first power, 2 minus 1, and by convention we don't write that 1 in. So now let's check the units. Meters per seconds cubed times seconds. So, oops, we can just cancel 1 of those seconds here, and we'll get meters per second squared. And that's why I like writing the units the way I do, because it tells me, yes, I did all of my derivatives the right way, I didn't accidentally do an integral, and I end up with the right units. So if this is my velocity, that's my acceleration. Now let's find position. Now for position, we had that velocity was the derivative of position. So that means that position must be the integral of velocity. So we will go ahead and do the integral of this velocity, -2 units meters seconds to the third times t squared plus 1 meters per second. All right, and so integrals, we do the opposite we do of derivatives, and so that means we'll just keep these guys along for the ride. And t will go up 1 power, so it will be 2 plus 1, that's 3. And then we divide by the new power, 3. And then this guy, well, we don't have a t here explicitly, but that's the same as having t to the 0 power. So we have our constants are all there. T to the 0 plus 1, that's 1, divided by 1, that's 1. And then we have our unknown constant, c. So if we simplify all of this, I'm just going to erase it because I've run out of room. I would have -2/3, so -2/3. T to the third, just write that in at the proper height. 1 and 1 and 1. So we'll keep the 1, but just make this a t plus a constant, and we don't have enough information yet to figure out what that constant is. But we can see, like, hey, if I knew where position was, where whatever I'm looking at was, when t is equal to 0, if I plugged in t equals 0 here, that whole term would be 0, and if I plugged in t equals 0 here, that term would be 0. Both these terms would be 0. So in this particular instance, and in fact usually, but not always, this constant is going to be the initial position. And that only happened because every other term had a t. So when I plugged in t equals 0, our start time, or at least when we started the clock, not necessarily when we started looking at what was going on, both of these terms became 0, and the only one left was this constant.